So without going into too much detail, I'd like to invite Anthony up to the stage so he can take it from here. Thanks.
All right, I guess you can probably maybe tell I'm a mathematician because I'm going to use a whiteboard, and if we had a chalkboard, I would use the chalkboard. So I hope Muthu's presentation is going to be really nice in comparison. All right, so here we have our company, what's that called, subhead thing, discover what you don't know. And on the technical side, I think we have a little bit of a different saying, which is that, and if you remember one thing from what I say, this should be, so data has shape, and shape has meaning. So this is sort of what drives our analysis, is understanding shape and meaning. And that's what I'm going to talk to you about is how we, I'm not going to focus so much on how we create the shape from data, but I'm going to focus on how we extract meaning from shape. What does that mean? And I'm just going to keep this up here. And so let me just say a quick bit about the part I'm not going to talk about. So how do you create shape from data? Well, one is you choose a set of features or columns to measure about something. Columns depending on your perspective, and then you have a metric on those features. We actually don't need, so a metric is just some notion of how far away something is or how close something is. We actually don't need the full strength of a metric for anything that we do. We just need a notion of close. If you know what's close, that's good enough. The far things are far, you don't have to worry about exactly where they are. But you can just, if you're worried about it, it's just some data. We just have data points and we have a metric on them. All right, so how do we create meaning? How do we extract meaning from the shape once we have it? So the basic setup is, I think, something we're all familiar with. We have lots of points, right? This is big data, lots of points. And the points have lots of features, or another way of thinking of that is that maybe high dimension. There's a high dimension ambient space that everything's sitting inside of. And what's the problem with this is that the shape, this first thing that I said that's most important to us, the shape is inaccessible. We can't see it, it's hard to touch, maybe it's poorly sampled. So the big problem is that the shape, so that the shape is inaccessible. So that's from several factors, too many points, or the dimension is too high for us to visualize. Another way of thinking about this, inaccessibility, is that there are too many stories in our data. So this analogy is the room full of people like we just had, where everyone's talking at once, and you walk in, you can't hear anything, it's just white noise. And what you want is some ability to zoom in on an individual conversation or on a group of people having a conversation and to understand what that group is saying. And you want to do that in a way that doesn't distort what they're saying, right? The whole conversation is still happening, but you've zoomed in to that little piece of the conversation. So the big data problem is also one of too many stories. So white noise in a room. Another way of thinking about it is we deal with a lot of biology data. If you have, let's say, gene expression for a group of people, gene expression levels, which is a measure of all of their genes, how they're acting in some situation, there's a lot of story. You're interested in, say, cancer, but there's a lot of stories going on about just regular cell activity, about all kinds of things in that data set about gene expression levels. And you want some way to zoom in and grab that cancer story or grab that whatever that other story is to make your analysis. So that's another way of looking at this. I'll just write gene expression data. So that's that's what we want to do. We want to zoom in and pick out the relevant aspects of shape for the question that we're trying to answer. We do that, so the way we do that is via, so how do we do this? We do this, it's via topological summaries. Okay, and I don't actually, I forgot to read the word topological. Yeah. I actually don't like really topological summaries, although it's okay. I don't like the phrase because it's sort of, you know, well, we'll leave it at that. We'll just leave it at that. Okay, so how do we do that? So I'm going to work one example for you, and I'm actually not going to do it the way we do it in our software, the example. I'm going to say quickly at the end how you adjust what I show you to the actual software. So my presentation, I'm going to do it in the world of mathematics here, where things are continuous, where we have continuous functions, and we have a continuum creates a shape. So here's my pair of pants, and yes, they are upside down. That's just how I draw them. So we have our pair of pants here. So how am I going to create my summary? So we do that with what we call a lens. And a lens, from this perspective, and I'm going to try not to be too mathematical. I'm mostly going to stick with pictures. Those of you who might be getting nervous that I'm about to do something with a lot of Greek symbols, I'm going to try and stick with just the pictures. A lens is just, for the sake of this discussion, a continuous function. Actually, doesn't have to be continuous, but let's just stay in the sane world. And so how do we use that to create a summary? Well, I take a point P in the image of the lens, and I look at the set of points that map to P. So I call that set F inverse of P. And I'm going to collapse the connected components of the inverse image and draw a single point. So here, my inverse image consists of a circle. The whole circle is connected, so I collapse it to a single point. I'm just going to go over here and draw that point. All right. Now, I just go over the range of this function, and I just do that for all the points. So starting at the bottom, I have a single point. But look, when I get up to here, at Q, F inverse of Q has two connected components. There's two pieces. So I'm going to draw 2 points up top here at Q. Let's go down and connect. So this now, so I took my shape. So my shape, which I'm imagining here, I've drawn a pair of pants, but you should imagine it's inaccessible. We can't see it. But what we do have is a continuous function on that shape, which is just a number for every data point. That number can come from a lot of sources, and I'll talk, sort of a key part is, well, how do you generate these Fs? And at the very end, I'm going to tell you something about where we get these functions, these numbers, to create nice shapes, nice summaries. But I take the shape, the ambient shape that we can't see, even though I drew it, the function, and I produce a summary. What is this summarizing? This says that my data has one piece and then it splits. It's not this isn't that complicated of a set. The summary is pretty simple. Well, let me do another summary. I'm going to have to redraw my pair of pants. So let's do that. I'm going to redraw my pants. And I had this one that I just did, which gave me my Y. Now I'm going to take another lens, another function, which is going to be the just projection, well, not exactly projection, but just this map here, where above this point is whatever sits above this point over here. Let's pretend like this whole, anyway, yeah. So here, I get this whole line here, so it has one connected component, so I get a single point. If I move a little bit in this direction, I have this line on the front and this line on the back. So I have two connected components. So this single point split. as I go along, when I get here, I again have one connected component, because it just goes up and down the back side. So this will meet up again. There's a region here where I have one connected component, and then here again, by symmetry, I end up with another circle. So this here is a different lens on this data that's produced a different summary. It's told me something else about the data. This summary said you have a part that's one part and then it splits. This summary says you have two circles, right, connected by something. Each of the pair of pants is both of those things, right? But I've extracted one piece of information with each summary, one interpretation. And that's basically, in a certain sense, I could just end here. That's what we do. We take data, we take functions, we produce summaries. The summaries tell us something about the data. Something to notice in this procedure that's really important when we compare it to other machine learning methods is that we've made no assumption about the data, except right at the beginning here, this notion of closeness that comes from the metric. So a lot of machine learning techniques make some kind of assumption, a statistical assumption, a geometric assumption about, say, linear separability, or about some other notion of something. We've made no assumptions about our data. And that's a real distinguishing feature about what we do. And this seems very simple. Of course, the really astute here are thinking, but where did that come from? Right? It clearly relies, if I just choose some random function, my summary might not make sense. So key is obviously going to be the choice of these functions, the choice of our lenses. So having come from academia not that long ago, I'm going to give you an exercise now, homework assignment. So here, and we'll see, and people from Ayasdi can't answer. So here's the exercise, which is what is the summary if we use both lenses at the same time. So what do I mean by that? Well, I mean I have my pair of pants upside down as usual. And now I take the map here, F1 and F2, right, where I can call this one F1, and this one, which I call G, I'll call F2. So I take F1, F2, and I map instead of to the line, now it maps to the plane, and I looked at the connected components of inverse images of points. So what's the summary?
I want to back up.
You want to back up?
Yeah.
Did I give that option?
No, but I'm taking a.
All right.
I want to imagine, I'm looking at this pair of pants. Is this a model where we have, say, 3 dimensions and our data points cover the whole surface of the
That's
pants?
right, yes. If I didn't say that, I should have said that. Yes,
Okay.
exactly.
And we're assuming that the points are dense enough that it would really look like.
I'm
that
actually
pair of
assuming
pants.
just continuity. This was math world. So I'm assuming that this isn't data world where things are discrete. This is math world where they're continuous.
Where you have an infinite number of data points. in
That's
the shape
right.
of those
It's
pants.
a manifold if you want, a manifold with boundary, if you like those terms or not. But it's infinitely, there's infinite number of points, it's smooth, it's connected, whatever you want.
Okay, thank you. I don't know the answer.
So the dimensionality of that space is the same as the number of the columns in what you just erased up there?
So in this case, the dimensionality of the ambient space is the number of columns. But but you're not supposed to, this picture is supposed to, this is a stand-in for any any complicated thing.
For this one, it would be a light.
No.
A light.
A line? Nope.
Wouldn't it be the pants themselves?
Yes, we get back the pants. It was a trick question. There is no summary. We recover the pair of pants itself. So that says that with a rich enough, so the lenses were producing summaries, And it says that with a rich enough set of lenses, you can recover the space entirely. And, well, that's heartening in a certain way, because it says we can choose, right? We can choose the level, how much of the space we want to recover, how many stories we want to pull out, how much information we want to extract by the lens choices and the number of lenses that we apply at the same time. So we can recover the whole thing, right? This is a very simple space, right? In general, we deal with problems where 2 lenses aren't going to work, right? You need tens of thousands of lenses. But in principle, you can recover the whole space. But let me caution you here, that's not the point. Recovering the whole space leaves you exactly where you started, which is that you have this thing you don't understand, that's too complicated to understand, and you want to summarize it. So what we do is we choose a small selection of lenses to extract the information we want. And let me just show you pictorially the kinds of things that we do. So here we have our pair of pants again, and we have our lens. And let's say I'm interested in this group of people right here, or this collection of points. For some reason, whatever, these are the people that buy my product, these are the people who have cancer and survive, these are, right? There's that group of points is the points I'm interested in. What happens with our lens, right? We have our lens here. This is our output that we're going to be looking at or analyzing. In our output, those group of people go to this region of the space. So we can look at this region of the space. We know now where to find our people, or where to find the customers that we're interested in. Yes?
So we don't really know at the beginning where they are, and we're trying to find
That's right. We don't know where they are, but with a good lens, and obviously I've chosen a region that will get localized under this lens, right? But maybe we don't, that brings up a good point, maybe we don't have to be so careful about our lens, because with this kind of localization, if I look down here, well, they're also localized. And in fact, with almost any lens I choose, this group of people is going to be localized in some region of the output, right? So I have this low dimensional summary, or this sort of compressed summary where the thing I'm interested in, I can see exactly where to find it.
When you say localized, do you mean if they're sufficiently close in that, and they're going to be sufficiently close in that one?
Yeah, that's sort of what I mean. That's what I mean. But I mean something a little bit more than that. So for instance, if they're localized in this way, so here they're not really all close. This is a different kind of localization.
Okay.
I'd prefer not to have to define localization, because I mean a lot of different things. But if they're like this, and to just stay not technical, let's just stick with the pictures. Well, what happens here, again, they get localized to a region, but in this map, they go everywhere. So depending on your problem and your lenses, my point is that you have sort of a space of things to explore, and typically in a lot of situations what we're interested in are these localizations and finding lenses that do that localization for us. So that's a very typical problem. So let me just say now what we do. So this is Math World. I'm going to tell you just in words how we go from Math World to Data World. Not because I don't want to tell you, but because I've been told that I have to keep my talk reasonably short, and it just takes too long to actually draw it out. So problem number one is that in Data World, if this is a finite collection of points, no matter how densely sampled, if I take the inverse image of a real number, most of those inverse images are just going to be empty. There's not going to be anything in them. So instead of taking inverse images of points, I'm going to fatten those points to be open sets on the range. I'm going to look at those points that are in inverse images of open sets. Okay, so that's problem number one I had. Problem number two was I took connected components of the inverse image. Well, everything in the inverse image in a discrete set is disconnected, so I have to solve that problem. What I do is I do clustering on that inverse image. Not on the whole space, but just on those points that are in the inverse image, and the clustering defines the connected components for me. problem number 3 is that I was able to connect all these points just by moving continuously up, but now I have the space cut into open sets. How do I know how to connect my clusters together? Well, I'm going to connect them together. Well, what I'm going to do is when I do my open set fattenings here, I'm going to make sure that they overlap. So there's some open set that's on the overlap. Then when I take inverse images, I cluster, and then because there was an overlap, there are points that were in both here and here. So that means those points are going to end up in some clusters up here, some clusters down there. I'm going to connect them. So let me just draw that really quickly. What I said in words, I'm going to draw what that means now. So here I'm going to take 3 open sets. That's 1, 2, 3. So 1, 2, 3. I'm going to look at the inverse image. I have all these points here. I'm going to cluster them. So I'm going to draw a point for all the clusters I find. I'm going to assume here I find 1 cluster. So I draw a point. I do the same thing for this inverse image. So it goes from here to here. This next one. I cluster them. There's 1 point. But because of these points that were on the intersection, I'm going to connect those clusters because they have shared points. Now I go up here, I have points here and here. These cluster into 2 groups, so I have 2 clusters. And then again, I had points on the overlap that tell me that this connects to this. So this here now is the summary that we produce in Data World. It's nodes, where the nodes represent clusters connected by edges, where edges represent shared points between clusters that come from overlaps in the image space of the lens. So that's what we do. That's sort of almost exactly what we do. So now there's just one detail left in this story, which is, where do our lenses come from? Right? I mean, just do random functions work? Right? What do I say? I keep saying continuous, but in the data world, in the smooth, in the discrete world, well, do I really want to work to figure out how to define a continuous function on a discrete set that's sensible, that makes sense for me? And the answer is,
Wait a second first. What allows you to assume continuity in your overlaps?
so the image space is the real numbers. These are, okay, so I didn't say, let's just say the image space is the real numbers, and I take these overlaps. So it could be that the overlaps are empty when I look at the inverse images, and we allow that to happen. That just means, I don't draw an edge and I get a disconnected graph as an output. So that's one thing that we allow. Another thing is we don't get pedantic about continuity or worrying about continuity. That's another sort of thing to keep in mind.
Do you assign weights to these edges?
Nope. Nope. An edge is an edge. Doesn't matter how many points. Yeah, it's tempting to get really complicated with weights, but no, it actually works. This is the way it really works well. I know. It's an obvious thing to think of.
How do you define the open sets? How do you define the open sets?
So the image of these functions, well, the images can actually be any other space, right? But we usually take the real line and we just take intervals on the real line.
Right, but I mean, you could take that. Do you take random intervals? How do you define what?
Oh, how do we define? We have some way of doing that. Usually, we do it either where they just are equal sized, or we size them so that the inverse images have equal size. And that's kind of our 2 methods that we use, and they work well. You could do anything you want, and there's reasons why you might want to choose other things in some cases, but this works actually really well for what we look at.
What's the difference between dimension reduction and topological summary?
That's a good question. The output here is actually an abstract simplicial complex. It doesn't really live anywhere. It's not really dimensional reduction at all. So dimensional reduction you usually think of like something like isomap or MDS, where you're trying to find a low-dimensional approximation to some collection of points, and that's like the output is this network has no metric on it. It's no, you could do lots of different ones. It's not. It doesn't even really live in Euclidean space. It's just like it's. We display it. We have an algorithm for displaying it on in our software that's very good. It makes it look really nice, but it doesn't really live anywhere in particular. So it's not dimensionality reduction. So I was going to tell you about our lenses, but I'm running out of time. So, well, I've got a schedule here too. I've got a 2-year-old at home. He's getting hungry. There's all kinds of things that maybe not everyone's privy to. Okay. All right. So, the point is that lots of people have actually. So lots of people have already come up with lenses for us. And they just didn't know that they were coming up with lenses. So statisticians, might be some of you in this room, have been working for hundreds of years coming up with lenses for us. So things that we can use are the mean of the row, right? If your columns all have some nice property where it makes sense to take the mean or the variance or maybe the entropy of the row.
So it doesn't have to be multivariate, it can just be single variate.
That's right. That's right. We're just taking the row and we're doing simple statistics. I'm going to call these people machine learners, but it's really statisticians or like modern statisticians, neo-statisticians. And maybe some of you will disagree that it's even should be here. PCA creates a lens just by taking the value of the eigenvector at that point as the value of the function. And like we said, MDS, isomap, and there are more things we can do here. We can do things like if you have say a support vector machine that you really like, you could take distance from the separating hyperplane as a lens. That's a legitimate lens. So I'll just leave that in the dots. And then geometers have come up with lenses for us. And one that really works well for us is centrality, which is a way of measuring how far points are away from the center or the core of points. The only sort of trick with it is that our points aren't really embedded in Euclidean space necessarily, so we don't have like center of mass, so we have some way of dealing with that for abstract metric spaces. And there are more dots here, and then there are also domain experts, meaning you're studying some problem and you can assign numbers to the objects that you're studying, but maybe you don't use these numbers to build your space, but there's some ancillary thing. Maybe you have a social network and you have the age of all the people in the network. You could use something like that as a lens. So there's
business key performance indicators kind of thing.
You could use, yeah. So the point is these all plug into our framework for machine learning. All these different all these different techniques, and the networks, and they also provide ways of interpreting the networks that come out. So that's how we get meaning from our networks, is by the lens values that come out of them. And let me just say, let's say I had this as my output network. It comes from some space that I don't understand, X, right? It produces this network. If this were a centrality lens, and these were the least central points, this says I have a central core, and there's sort of two ways of being odd. If this were a domain expert, let's say I'm studying cancer, and this here is the age of the participants, this says when people are young, there's one kind of cancer, and then when they're old, there's two kinds of cancer. So the lens that we choose gives us the ability to interpret the summary and understand something and gain insight about our data. So that's what we do. Data has shape, and then the shape has meaning. And we've told you what it is. All right, thanks. All right, questions?
The name topological data analysis, topological means the thing that you get out of it? Because none of the things that you're talking about, the lenses, necessarily have anything to do with topology.
Well, I did say continuous, which is... So, there's a number of ways of analyzing that. So, one way of generalizing what we've done is you can view this as, I'm going to say it, and I really just, you go Google it, is as the second projection of the Meyer-Vietoris blowout. I said it, now let's move to the next question.
You can also say that we're driving local information to get global understanding, which is core to topology.
Okay, yeah, fine. Thank you, Jennifer. Jennifer is a topologist who works with us, and she's right. So what do we need? All we need is local information, which is to say we need some kind of notion of an open covering of the space, or in the data world, maybe just a covering of the space, and that's the idea of an open covering is core to topology. You can also view this as kind of a realization of a check complex with respect to some covering, where we're using the lenses to create the open covering, right? What do the lenses do for us? They create open coverings of the space, and then the network is the check complex of the output. So there's a lot of ways that I sort of purposely didn't mention because I've tried to just draw pictures. Yeah.
So it seems to me that all the hard work is in finding the lenses and creating the lenses.
Yeah, but other people do that for us.
The insight, well, all the work's there, and even the insights seem to be based on how those lenses were chosen.
That's right.
So what does topology add to the picture?
Well, the topology is the machine that tells you how to go from the data to the insight.
No, but if you, as you said, if age is saying that there's a diversion that.
But we got this from the
If you had to
topology.
do a lens by age versus cancer occurrence, then you already have that information. What is?
No, because
your
for instance, we have this network X might come from gene expression levels for cancer patients, and each patient has 20,000 numbers associated with them, gene expression labels, and I have 5,000 or whatever, 100,000 patients. So I've taken all that information, which is completely inaccessible for understanding, and reduced it to this Y, where now I can tell you, using the proper lens, where now I can tell you there's one kind of cancer here and there's two kinds of cancer up here. Or I can tell you, maybe these people all survive and these people die. I can say, down here there's a mixture of death and survival, but up here I can say this group of people, and I can trace these back with the inverse image and tell you who they were, are going to survive based on those genetic markers that they have. But the space here was inaccessible, and I needed topology to create this summary.
But that depended on choosing that lens appropriately.
That's right. So we have a lot of lenses that we built into our product, and we actually have a mechanism for automatically searching through the lens and metric space to help find and pull out the interesting networks that will hopefully tell you. So like, yes, a domain expert can do this, but we have a way, we're turning the crank secretly behind the scenes, and we can guide you in this process. And the other thing is that a lot of problems you don't actually want insight. You actually stop before the interpretation step. Say you just want a classifier. You can build a classifier using these techniques. A classifier doesn't really give you insight in the same way that the network does, but you can build a classifier and you just never get to the insight step. So you can also do that.
It's basically pre-processing. If you're feeding it into a classifier.
No, we can actually, you could actually, you could build a classifier with the network itself, but by the kind of, Then there's the next step where you attach something to the network. Sure, that's fair. Yes.
So how do you define when one lens is more discriminating than another?
It's complicated.
So all of the lenses are providing very real views of the data, right? And some of it depends upon your specific goal. Our idea here is that each of those lenses, and like Anthony mentioned, we have a quick analysis feature that's going to give you a number of suggestions. You get to take a look at those suggestions and identify whether the shape that you see is correlated with aspects of the data that you're interested in. So they're all representing real aspects of the data, and you can explore what different structures that come out of the different lenses represent. They might answer different questions, right? So there's cases where L-infinity, the centrality lens, for example, will give you an answer to a question that's different than some of the other lenses that come up.
And so coming from a stat world, how do you say it's significantly discriminating? I mean, how can it is a fluke or a not fluke?
Okay, and so that's why, you know, the graph that comes out, right? It's kind of here's something that's interesting that's come out of this analysis framework that Anthony's described, and then on top of that we have a suite of statistical exploration tools to allow you to explore the significance.
Thank you, Alexis. Yes.
My question is about the overlapping of the lenses. Like, if they're all different lenses, that is, if they all have a different metric, then wouldn't there be some kind of disconnect in the overlaps of them? Like,
so the lenses aren't the metric. The lenses are functions on the data. So if you have multiple lenses, you just end up in the product of their image spaces. So when I had two lenses, when I had one lens, I went to R. If I have two lenses simultaneously, I go to R2.
So they're all with the same metric then, like one of these statistical metrics, for example.
Oh, this is what you mean by metric. Each lens can be a different function. So for me, these are just, so the topological machinery just eats functions. So I just view the mean of a row is just a function on rows. From this perspective. When I go to interpret it, it becomes important what that lens is, but just view it as a function. And then I have some other function. I use, as lenses, I could use mean and the third isomap coordinate, if I wanted to. Right? Yes?
So just to try to get the general program here, you're using the lenses to try to create a topology. So, you know, Klein bottle, torus, whatever, how they're, depending on how they're interrelated, and you can like put together the pair of pants, or are you starting it with some kind of topological guess and then choosing the lens on that basis to, I mean,
so there's no, so the data, the part of this saying up here that I skipped was the choice of the metric. So, and like I said, we don't actually need a metric, we just need similarity or something. So that comes as part of your problem. And that's up to the person posing the problem to decide what does it mean for something to be similar to something else? What does it mean to be close? And we can't decide that if you just give us a bunch of data. We can try a bunch of different metrics, and that's something that we do. We just try metrics and we try lenses and we pick out the ones that are interesting. But if you want to sort of run through the process by hand, like just once, you have to choose that metric to begin with, or that notion of similarity.
how does the notion of cycle come into it? Because topology is all about cycles, right?
So topology is about a lot of things. So like homology or cohomology is sort of one aspect. That's something that we're in the process of building into our product. There's something called persistent homology, which is a sort of an adaptation of the concept of homology and cohomology and things like that to the data world, to the topological world. I haven't discussed that at all. That's not a part of this machine that I've described. It's something that we're working on independently. Yes?
You mentioned that there's an intermediate clustering step, and I'm curious how sensitive the outcome is to what happens there.
It's not very sensitive. So that's not quite true. Of course, it matters what these clusters are. Yeah. But one way of viewing this is that these lens values, if they're sort of small enough, these inverse images, you're only looking at a piece of the data. And those pieces are easier to cluster than trying to do the whole global thing. So you could use, it's a lot less sensitive to the clustering mechanism. And let me just draw a picture of what I mean by that. If I want to cluster, so if I want to cluster two circles, right, and let's imagine, right, this sort of classic example, I have noisy circles. This can be a hard problem sometimes to do globally. But if I use as a lens any projection, and I look at the inverse images of open sets, right, these are actually a lot easier to cluster, right? The inverse image, I sort of have these, this is easier to
That's
cluster.
a really nice property.
So by slicing it up, it's a lot less, it relies less on the clustering than you would think. And I didn't emphasize the clustering step, and part of the reason I did that is that when a lot of people hear the technique the first time, they end up coming away thinking it's some kind of clustering technique. But clustering is just fulfills this one thing of finding connected components of the inverse image force, which is just a small piece in the machine. So I didn't want to emphasize exactly what's going on there too much.
How do you choose the slicing? Like how much you're slicing by?
That's a good question. So the slicing actually provides resolution on the size of the topological feature that you're extracting. So in this case, I've extracted actually everything with this very coarse slicing. If I make my thing smaller, I just end up adding intermediate nodes where some of the points, right, they get spread out. If I don't have it coarse enough, I end up with something like this. And if it's really just one set, right, I have this. And so as you increase the resolution, we call it, or make the sizes smaller, you go this way, you pull out more details from more topological details. So the level, sort of the details, that level is to some degree up to you, sort of what is useful for your problem. Where, at what level of resolution, the things that you're interested in, where do they lie?
Let's do one more question, then we'll move on to Big Data.
Is there a bad metric that would be, maybe like profitability? Everything would have a grayscale on profitability, whatever you're selling, your transactions or your services. And so, across the range of age of customers, there's some level of profitability, whatever other fields, but there's never any missing. So it seems like everything would collapse down to one point. You wouldn't get a Y fork, you wouldn't get the barbell shape if there's no, that everything would keep collapsing down. Would that ever be a problem?
I'm not sure actually I understand your question. Maybe.
I think his metric is a lens.
Yeah.
Are there lenses
Right.
that everything collapses? And yes, sure. I mean, you can choose bad lenses. I mean, if they give just a constant function, I'm not
Yeah.
sure you get any resolution out of it.
Yeah.
Okay, so if it's big as a continuous number but never any zeros, then everything's going to be fully connected and reduced to a point.
No.
As
Oh,
long
okay.
as there's a range, then
Oh, okay.
those things are good.
Yeah. Okay. All right. Thank you.